Hi all, I'm Marcin and welcome to my presentation on QUIC DoS attacks. This is joint work with Raphael, Thomas and Matthias. So QUIC sees an increasing deployment. Large content providers rapidly transition to QUIC. To prevent harm in the web ecosystem, we should identify attacks as early as possible. And that's why we've investigated whether QUIC DoS attacks are a real threat. In this talk, we tackled the question, is QUIC used for DoS attacks? And the short answer is yes, it is. And the nice thing here is that network telescopes allow us to observe these attacks. So by implementation, QUIC is based on UEP. It looks like regular UEP traffic, which makes it more robust to ossification or manipulations by middle boxes. However, by design, QUIC has some similarities with TCP. It is connection-oriented, so we have a handshake process, and this is important for this talk. Let's take a look at a typical QUIC handshake. So the major design goal was to reduce round-trip times. Before, because of independent TCP, TLS and HTTP handshakes, we had at least 3 round-trip times, and now we have 1. It all starts with the client sending an initial message, then the server responds with a server hello and a handshake message containing TLS information. Then with the second message, the client adds the last bits of its TLS information, but is also already allowed to attach a get-getter, so already after the first round-trip time. The server then responds with the encrypted data. Alright, so what's the problem here? Well, during the first round-trip time, the server responds to an unverified source. This means that the server responds to a potentially spoofed client IP address. This makes 2 different attack types possible. First, reflective amplification attacks, which are currently unlikely because QUIC's amplification factor is very limited, especially if you compare QUIC to other UDP-based protocols such as DNS or NTP. However, there's also a second type, which are state exhaustion attacks. Let's take a look. Here, the attacker randomly spoofs client requests so that they look like many different connection attempts from multiple clients, and all these requests are sent to a single QUIC server, which then is overloaded because it reserves resources for each individual connection and also has to perform cryptographic computations due to the TLS handshake. So we have a server-side resource exhaustion because of QUIC initial floods, which, as some of you have probably noticed, are similar to a TCP SYN flood. As a side effect, as long as the server is not completely overloaded, it will try to respond. And since the IP addresses are randomly spoofed, part of the responses arrive also at measurement networks called telescopes. Over the last decade, researchers inferred TCP SYN floods using telescopes, and we extend these measurements for QUIC. Again, telescopes are fully passive network segments which record all incoming traffic. This includes scan traffic, misconfigurations, but also anomalies from attacks such as DoS backscatter due to spoofed traffic. We use data from the UCSD telescope, which covers 1 month. And since we receive various traffic types, we have to detect QUIC. We use Wireshark for that. This means that we detect packets based on the payload and not only by ports. Then, as a second step, we classify the packets into requests and responses. We expect QUIC requests to originate from scanners, and responses should be backscattered due to QUIC initial floods. And that's what we found. In this plot, we see the number of QUIC packets per hour. We see that QUIC requests, that's the blue line here, actually have a rather stable diurnal pattern with peaks at 6 AM and 6 PM, as highlighted in the inlet. But the response traffic, that's the orange line here, is very erratic. It exhibits high peaks and drops despite the logarithmic y-axis. Seeing such a high volume of responses in a short time, which then vanish, already hints at DDoS attacks. That's why for all these individual backscatter packets, we then try to infer significant DoS events. We rely on an established method, which was previously used for TCP SYN floods. Basically, we group packets into sessions or flows with an idle timeout, and then we apply thresholds to find QUIC backscatter sessions with large traffic volumes. Overall, we found 2,900 significant attack events in April, or 4 attacks per hour. And 58% of these attacks target Google and 25% target Facebook servers. But that's only the top-level statistics. We also looked at single victims in detail. So this plot shows backscatter DoS events for a single victim server. We see roughly 4 hours, and we highlight here when a TCP or a QUIC attack start and stop. That's the red and the green triangle. And between 2 and 3 p.m. we observe a multi-vector attack. This means that the attack consists of at least 2 attack traffic types. Here we see a concurrent TCP SYN flood and a QUIC initial flood. Then later we find multiple QUIC attacks which happen after the TCP attack or in sequence, and that's why we call them sequential attacks. Surprisingly, this observation was not a single case but a trend. For 51% of QUIC attacks, we found an overlapping TCP SYN flood attack. Another 40% of QUIC attacks happened before or after a TCP attack. And only 9% of all the detected QUIC attacks were completely unrelated. As the last part of this talk, I want to introduce you to the QUIC retry message option. Retries are very much like TCP SYN cookies. Before the server reserves any resources, it responds with a simple token. Then the client must come back with this token, and only then the typical connection handshake, as described before, is initiated. This proves that the client is real, but adds a full round-trip time to the connection setup. So we wanted to check whether retry messages can really protect QUIC servers. Therefore, we built a DoS testbed. We run QUIC initial floods at different packet rates, that's the leftmost column here, and we started our test without the retry option. So this is indicated here by the rightmost column. And we find that already 1,000 packets per second can lead to service degradation. Then we used all CPU cores at our server, which helped. The server handled much larger packet rates. However, this only delayed the problem. As a third measurement, we activated retry messages. The service was reachable in all cases, so the DoS attack was prevented, and retries proved themselves to be effective. But although retries are so effective, we find that they remain largely unused by well-known content providers, at least for now. So let me conclude my talk. QUIC initial floods are an actively misused attack vector, and we detected and quantified these attacks with a network telescope. Future directions definitely should include the fine-tuning of DoS detection thresholds, but we also want to find out whether permanent retries are worth the cost for content providers. Thank you.